Welcome to Inside IHE International Webinar Series, Introduction to the New Personal Health Devices Observation Upload Profile. I'm Tom Erickson, Director of Technical Operations for the PCH Alliance. I will provide a brief background on why and how the PCH Alliance and IHE International align their profile development efforts. Brian Reinhold, Domain Expert at L&I Health, will then provide you with an overview of the first profile that was developed as a result of this alignment. The COVID-19 pandemic has demonstrated a clear and urgent need for the continued monitoring of patients' vitals at home and in the hospital. Using the same technologies to capture and upload these vitals is critical to rapid and efficient triage as patients' conditions worsen and merit the use of scarce hospital resources. Remote patient monitoring offers a method for patients to proactively monitor their condition at home while staying connected with their healthcare providers and provide fair warning if or when their condition warrants admitting to a hospital. In-clinic remote monitoring provides patients with a way to continue monitoring their condition while limiting exposure of staff and saving scarce hospital resources. This monitoring of a patient's condition must continue seamlessly from home to clinic to hospital, without the distraction of staff intervention to transition from a home-based to a clinic-based technology, or from one vendor's monitoring solution to another. The Personal Connected Health Alliance focuses on personal technology with a patient consumer-centered approach to improving health and wellness. Integrating the healthcare enterprise promotes the coordinated use of established standards to address specific clinical needs in support of optimal patient care. Profile development activities in the PCH Alliance were moved into IHE International to develop and promote technologies and standards that enable a more seamless experience between hospital and home. This is most important for the patient, but common technologies also increase efficiencies at the clinic. The personal focus of PCH Alliance and the clinical focus of IHE International were aligned under a new IHE domain called Devices. Under the Devices domain, there are three programs. The Patient Care Device Work Program, formerly known as the PCD domain, is concerned with the use cases in which at least one patient-centric point-of-care medical device or information system communicates with at least one other medical device or information system. The Device Point of Care Interoperability Program focuses on device-to-device interoperability technology that is optimized for high acuity environments such as operating rooms or intensive care units. The Personal Connected Health Work Program focuses on developing solutions for remote patient monitoring while harmonizing with technologies used in point-of-care medical devices. The first profile to be developed under the aligned program was the IHE Personal Health Devices Observation Upload. This profile describes a standardized means of representing personal healthcare device data as FHIR Resources. PHDs are typically used by patients at home and employ the same device information models and nomenclature codes as the point-of-care devices used in hospitals. New profile development activities focus on working with IEEE personal health devices to create a dramatically simplified information model independent of transport, working with the Bluetooth SIG to create a service and profile to communicate a wide range of health-related observations from health sensor devices to collectors, providing implementation guidance for observation uploads directly from a health and fitness server from a compute-constrained sensor. Brian Reinhold will now provide an overview of this PHD observation upload profile.
Thanks, Tom. In a nutshell, the PHD observation upload consists of two parts: transcoding the data obtained from the personal health devices to FHIR, and uploading that package to some destination. The typical scenario is from the home to the healthcare provider, but it doesn't have to be. The goal is to get PHD data to FHIR Resources, but there are numerous different types of PHDs, most of which do not follow any standard protocol. To ease this pain, we pretend that all PHDs follow the 20601 standard and provide certain objects containing attributes. The 20601 objects represent some feature, and the attributes describe that feature. We are only interested in the MDS and metric objects of the 20601 protocol. The MDS is an object that gives information about the device: name, serial number, firmware version, system identifier, regulation status, time clock and its properties, etc. The metric objects represent the measurements: temperature, blood pressure, ECG waveform, pulse rate, miles run, etc. The reason we use this 20601 representation is that it is generic. We only need to know about the objects and attributes. We do not need the attribute values in order to transcode the data to FHIR. There are only few objects and attributes, whereas there are hundreds of possible measurements they can represent. In fact, the 20601 metric objects can represent only 6 types of measurement values. Numeric, measurements that are given by a single number, such as a temperature or body weight. These are by far and away the most common type of measurement in PHDs. In fact, it's what most people probably think of when they think of a physiological measurement. And there's the compound numeric. These are measurements which are given by vectors, such as an acceleration with its x, y, and z component, or the blood pressure with its systolic, diastolic, and mean components. And there's the coded measurements. These measurements are given by one of a finite set of specified items, such as the activity of a training session, a run, a bike, walk, swim, etc. Then there are states and events types of measurements, a set of binary set cleared conditions that can happen simultaneously. An example of a state measurement would be the status of a patient's room in an independent living facility. Window closed, opened, heat on, off, lights on, off, patient in room, not in room, door open, closed, etc. Then there's a waveform. These are a sequence of periodic samples in time. A common example of a waveform measurement would be an ECG trace or a pleth wave in a pulse ox. Human-readable arbitrary strings are really not intended for machine processing, but just for direct human consumption. An example would be the name of an exercise program on a piece of gym equipment. We can illustrate this generic mapping strategy by looking at the most common PHD measurement type, the numeric. Let's take a look and see what is in the numeric object. Numeric metric object always contains at least 4 attributes. First one is the type. This attribute contains a code that tells you what the measurement is. Then there's the numeric value attribute. This attribute contains the numeric representation of the measurement. And there is the units. This attribute contains also a code that gives the type of units of the measurement. And last, the timestamps. This attribute contains the time at which the measurement was taken. We show 2 examples of how this generic measurement is encoded for a temperature and weight measurement. The important thing to remember is that any measurement whose value is given by a single numeric quantity can be represented with this single object. Spoiler alert, every numeric metric object will be mapped to FHIR in exactly the same way. So if we take a look at the temperature measurement using the generic numeric measurement object, we see that the type now actually has a value. It has a code, MDC temp oral. This code tells you that this measurement, 37.8, is an oral temperature. Well, the 37.8, well, 37.8 what? Well, we take a look at the units. And the unit shows that there's a code that if you look it up in some dictionary, you will see that, oh, it's degrees centigrade. And lastly, there's a timestamp, which is whatever it is. In the case of the weight, we have exactly the same attributes, decoded in exactly the same way. Now we take that code, we look it up, and we see, oh, it's body mass. The number is 167.8 instead of 37.8. And we take a look at the code for the units, look it up in a dictionary, and find out that it is pounds. And then timestamp is whatever the timestamp is. The nice thing for coders and implementers of the standard is that they use the same code to decode any type of numeric measurement. Clearly, the key to the generic construction is the use of codes. There are many coding systems in this world: LOINC, SNOMED CT, and for our model, the IHE 11073-101 nomenclature codes. The IE codes are chosen since they were designed specifically for medical devices. And in this slide, we show an example of some term codes from the Partition SCADA for the nomenclatures. Now, there are thousands of these codes, but you see that they are just numbers. The actual number that's sent over the wire is a 32-bit code, and this is given by the partition, which in this case is SCADA, and that's 2, and you multiply that times 2 to the 16 plus the term code. There are many, many more codes. Now that we have our set of 6 generic metric objects, let's see how they are mapped to FHIR. FHIR resources are also generic. FHIR resources are analogous to 20601 objects, and FHIR resource elements are analogous to 20601 attributes. The 20601 metric object maps to the FHIR observation resource. The numeric metric object maps to the FHIR PHD numeric observation profile. The observation resource, note that profile in this case is a FHIR profile, not an IHE profile. We can take a look at the detailed construction of this mapping, and we see that the type attribute, whatever is in that type attribute, that value is placed into the code element of the observation resource. Direct transition. They're both codes. So A goes into B. Every time it's the same way. And for the numeric value, it comes from the simple numeric value attribute, that is placed in the value quantity value subelement of the observation resource. Always done the same way. It's just one value to another value. The units are placed in the value quantity.code subelement of the observation resource. Again, that is a code. So it's a direct transfer of the code element of the attribute to the code element in the nomenclature code for the observation resource element. And the timestamp from that timestamp attribute goes to the effective date time element of the observation resource. Obviously, for the implementer, they implement the translation from a generic numeric measurement object to the observation resource following the numeric observation profile, and they do it the same way every time. So all you have to know is the numeric. If the measurement is a numeric, it maps the same way. In the end, there is a FHIR profile for each of the 6 metric object types, as shown here. These FHIR profiles detail how each of the attributes in the metric analog are mapped into the FHIR observation elements. The PHD implementation guide, which this IHE profile follows, describes each of these FHIR profiles. So it describes to the implementer how one takes a numeric metric object and maps it to the observation resource. You follow the PHD numeric profile instructions, etc. for each of the 6 cases. The generic nature of this mapping means that a gateway can blindly map these 6 metric objects to FHIR without ever knowing anything about what the measurement is. If a future device is ever created that detects, say, for example, what virus we might be infected with, the virus would likely be indicated with the new nomenclature code and sent as a coded numeric. A gateway written today would be able to properly map the data from that new device to FHIR without any updates. If a healthcare provider institution has thousands of remotely monitored patients, not having to update all those gateways to handle a new or different devices is obviously very convenient. To complete the POU profiles that are used, FHIR profiles, we have 3 others. Is the patient profile, and there's no patient information of significance on a PHD device. So this is more or less out of band and the responsibility of the gateway to set it up. Then we have the PHD device profile and the PHG device profile. The PHD device profile maps the MDS 20601 object to the device object, to the device resource in FHIR. And even though gateways do not officially have an MDS object or any object, 20601 object, we sort of pretend that it does, so that we can express the same type of information for the gateway as we do for the device. Some of the things don't make sense. But for example, a gateway might have a serial number, it might have a system ID, it might be regulated, it might not be, it might have a name, etc. And if you actually want to take a look at the FHIR implementation guide, it's available at the websites given here below. And the FHIR standard itself is also available at the websites given below. Now that we've done the hard part, we've created the FHIR resources from the measurement data and device data from the PHG and PHD. It needs to be uploaded to its destination. The POU profile specifies the Health and Fitness FHIR Service interface. It is a three-step process. First, the gateway does capability exchange, not to be confused with the FHIR capability resource. They're totally two different items. This exchange provides the URLs for the OAuth server and the FHIR endpoint, as well as the type of FHIR endpoint that the Health and Fitness server supports. The POU supports two types of FHIR endpoints: the classic FHIR server following the FHIR RESTful exchange, where FHIR resources are persisted, and a FHIR endpoint where the gateway cannot assume that the endpoint persists in the resources. The main difference is in the latter case, the gateway must send all of the resource associated with the measurement every time. Now, the nice thing about that is the capability exchange typically is done when the gateway first starts, and then it doesn't have to be done anymore. The OAuth server, this gives you the OAuth token. This authenticates the user or the application that is going to upload to the final destination. This depends on how many times the gateway must access the OAuth server. Well, that depends on the OAuth server itself. Usually an OAuth token has a lifetime. So the gateway must have some type of user or password to access the OAuth server, and this must be ascertained out of band. But once done, it queries the OAuth server for an OAuth token, and if it satisfies all the security associated, needed, and authentications needed, it gets a token. That token may have a lifetime. It may be long, it may be short. If it's short, it'll have to access it again. And once it gets this token, when it actually has an upload package to deliver, it associates that, packages that token with that upload, and sends it to the FHIR Health and Fitness server, whether it's a pass-through server or a persisting server. Finally, I want to summarize that the single most important aspect of the POU profile one should come away with is that the mapping is generic. It appears a lot of people have a hard time understanding generic principles. Every PHD whose data can be mapped to the 11073 metrics can be mapped to one of the 6 FHIR measurement profiles. This is regardless of whether the device follows the 20601 standard, which obviously will always work, or whether it follows the BT-SIG health profiles or is proprietary, which is the vast majority of devices. The nice thing about it is that it'll work for now and in the future, unless, of course, the standards change. Thank you.